Let's start the second session. I'm going to talk about summarization of sequential data and applications of it to learning procedures from instructional video data. So in the first talk, I gave an overview of components of subset selection. I talked about different objective functions to maximize in order to recover the set of most informative items. And I discussed that all of these are going to lead to NP-hard problems to solve. Then I talked about a couple of efficient techniques that can approximately solve the problem. And in the second talk, actually, Amin talked about the big class of optimization techniques based on submodularity that cover many of these criteria. And he talked about approximation guarantees of these techniques. It turns out that to do better optimization, to do better summarization, we want to get closer to the global optima. And what I'm going to do in this talk is do something opposite to what Amin did, which is he talked about a very big class of methods. I'm going to now focus on a particular class of objective functions called facility location. Then I'm going to talk about how we can develop efficient techniques to solve this facility location that can actually, under certain conditions, achieve the exact global optimal solution under certain conditions. Then I'm going to talk about sequential data, which are basically a big class of today's modern data set, whether they are videos or text or genes or signals or audio or speech, that they all have something in common, that there is this sort of a structured dependencies among the sequences of items. If we take into account, for instance, if we look at instructional videos and understanding instructional videos, we are not dealing with a bag of randomly permutable set of items. If we shuffle the order of the frames, we are going to get something which is completely meaningless. We want to extract summaries that are not only going to give us those key steps, but also the sequence of the key steps that needs to be performed in order to, for instance, achieve a certain task. So ordering in the case of sequential data matters. In the case of, for instance, text, which is another example of sequential items, there is basically a logical way that sentences come one after another, and you can basically throw away this natural ordering. And you should take that into account when you do summarization of data. So what I'm going to do then in the second part of the talk is talk about a generalization of the same objective class of objective functions that I picked in the first part, which is facility location, and generalize it to handle sequential data and summarization of sequential data. So that means that I'm going to develop a new class of objective functions and then efficient optimization algorithms to maximize or optimize this new class of functions. So let me start with the problem of subset selection without any notion of sequential structure. Assume that I give you two sets of items, one which I call a source set that consists of m elements. So I call X to be my source set, has x1 up to xm, which are m elements in the set, and another set which is a target set consisting of n elements, y1, y2 up to yn. And all I'm given is the set of pairwise similarity or relationship between every element of my source set and every element of my target set. So given these pairwise dissimilarities, the goal is to select a subset of my source that well encodes my target data according to these dissimilarity relationships. Okay, so the goal is I'm given this, I want to basically extract very few representatives from my source set that well encodes the target set. So this is a little bit different, or in a sense more general than the setting that we have discussed so far. Most of examples that we saw in the first session, where that you just have one data set, you want to summarize that single data set. So here we have two data sets and relationship between two data sets, and we want to summarize one according to the relationship to the second set. So it's in a sense a more general setting. So these Dij, which are dissimilarities, encode how well xi represents yj. So Dij, which is the dissimilarity of xi to yj, means how well xi represents or encodes yj. The smaller this value is, the better I represents j. And this is up to user to select this dissimilarity relationships and feed it to the algorithm. So when x is a set of data points and y is a set of data points, for instance, you can select Euclidean or geodesic distances as pairwise dissimilarities. When x is a set of models, it's an ensemble of models. These are ensemble of models. And y is a set of data points. Then, for instance, we can choose representation or encoding error of how well a model represents the data. And when they are, for instance, both models, we can select, for instance, distances between models, or if they are probability measures, for instance, KL divergence between probabilities. What we assume is that these similarities are not necessarily coming from a metric space. So they can be asymmetric, or they can violate the triangle inequality. And an example of why this is important is that, for instance, in the case of image encoding, this image on the left-hand side is a good representative for the right-hand side, but the reverse is not necessarily true. So we need to have, in some cases, in computer vision, this asymmetry relationship. So now, how we can recover this set of representatives? That was the setting of the problem. We have a source and a target, and we want to select a subset from the source set. So to do it, what we do is basically introduce these assignment variables, rj, which are basically encoding the index of the representative of yj. So we assume that every point in the target is going to be represented by one and only one representative from source, right? And rj denotes the index of the representative of yj. So these are unknowns that we don't know, and the goal is to recover this set of unknown representatives. So I have shifted the problem as to recovering these indices. Okay? So the approach that we take is then let's define a potential function that takes this set of assignment variables at its argument and is defined based on these assignment variables, and try to maximize this potential function with respect to these choices of assignment variables to select a set of representatives. So what is the right potential function? The potential function, the way that we define it is, it should be a potential function that encodes or incorporates how well the set of representatives encode my target set, and also we want to minimize the cardinality of this representative set. So for the encoding, what we are going to do is using the observation that since each point j is going to be assigned to one representative, we can factorize this potential function as a product over each of the elements from the target set. So we are going to have the product of n potential functions, that each potential says how well rj represents j. So if the dissimilarity goes down, which means that rj is a better representative for j, then ideally this potential function should go up, which is the case in this definition. But if I simply just maximize this potential function, there is a drawback that, I'm going to assign every point in the y to the closest representative with x. So I'm going to end up with many representatives, or a big summary. So what we want to do is to then minimize the size of the representative set from the x. Okay? And to do that, then we define this potential function, which is going to be basically exponential of some regularization times the cardinality of the potential, cardinality of the representative set. So, which is the number of distinct elements that we have. So if we select a large number of representatives, then this potential is going to go down. And if we select a small number, this is going to go up. So these two are basically have opposing forces. One tries to select more, that gives you better encoding. The other tries to select less, that gives you a smaller representative set. So there is going to be, at the end of the day, once we take the product, a balance between these two terms. So at the end of the day, as I said, we want to maximize this potential function psi over all possible set of assignment variables, R1 up to Rn. And each of these variables is going to take m possibilities. So we are going to have basically a combinatorial number of possibilities, 1 m to the n possibilities. So how we can effectively now solve this combinatorial optimization problem? So to do it, what we do is to change the problem into an optimization over a set of assignment or binary assignment variables. So what we are going to do is to define these new optimization variables, Zij, where Zij means that whether I becomes a representative of J or not. So if I becomes a representative of J, Zij is going to be 1, otherwise it's going to be 0. Okay? So it's a binary variable. So now, if we can manage to shift the problem into these binary assignment variables, we have basically gotten an integer optimization. So we can rewrite this potential function that I showed in the previous slide, basically using these new assignment variables into basically the product of these two terms, one that goes through basically every point in my source set. If I becomes a representative of J, I'm going to have an encoding cost of Dij. And if it's not a representative of Yj, I'm going to have an encoding cost of 0. So the encoding cost always can be denoted by Dij, Zij. So the overall encoding would be then to product over all the i's and go over all the j's. Right? So that's my encoding cost. And the second is basically trying to minimize the size of the representative set. And the idea is that, well, if I becomes a representative of some points, then at least one of these Zij's is going to be non-zero. So this vector is going to be non-zero, and the indicator is going to count 1. And if I is not a representative of anybody, this whole vector is 0, so the indicator is going to count 0. So at the end of the day, sum over I is going to count the total number of representatives that I have in the data set. Okay, so instead of maximizing the potential function, we can minimize the minus logarithm of the potential, which is going to exactly lead to this optimization, which is going to consist of two terms. One is linear in the assignment variables, Zij, and the other is basically this cardinality constraint term. That sums of the indicator function of these vectors that depend on Z. Subject to the fact that these must be assignment variables 0 or 1, and each point in the target must be encoded by 1 and only 1 representative. That's why we have this constraint of sum over I of Zij should be 1. And this is basically a formulation that at the end of the day is going to be related to the facility location or uncapacitated facility location objective function. I have started the problem from a different perspective, but at the end of the day, I formulated it in a way that now we have arrived at the uncapacitated facility location. Now this is an NP hard and also non-convex problem. So how we can solve it? The reason behind non-convexity is that, one, we have these assignment variables, which are just 0 and 1. So this is a non-convex constraint. And second is that we have the sum of the indicator functions that, as I discussed in the first talk, the indicator function is basically a non-convex function. So what we do is to now relax. So instead of looking at the indicator of this norm, we just simply use the norm itself. So we look at the sum of the norms, and we relax the integer binary assignment to simply be, in a sense, a probability. It's going to be an assignment variable which is going to be between 0 and 1. To what degree I is going to represent J. And this is going to be convex as long as P is bigger than or equal to 1. So for practical reasons, we are going to choose P to be 2 and infinite in order to get an efficient implementation. So lambda actually plays a trade-off, puts a trade-off between these two terms of encoding and minimizing the cardinality of the set. So let's look at these synthetic toy examples where my data is drawn from a mixture of 3 Gaussians, and then my blue points are the original points and the reds are the ones that the algorithm selects for various values of lambda. So for this lambda 1, for instance, I have selected these points. Once I increase it, at the end of the day, I'm going to select 1 point from every Gaussian. And then once lambda is sufficiently large, since we restrict that every point must be represented by 1 and only 1 representative, then we are going to get only 1 representative for the entire data set. And this is the structure of the Z matrix that actually shows this is really a clustering-based subset selection that, for instance, if I look at this, my first 20 points are going to be assigned to, say, point 19. My second 20 points are be assigned to point 42, and then my third 20 points are going to be assigned to this point 78, right? So this gives us the notion of clustering of the data. And in this extreme case, every point in the data set is going to be basically one cluster, that every point is assigned to one and one representative, right? So this is a convex relaxation, and I wanted really to solve the non-convex problem. I took a relaxation, and the question that we looked at is, when is it the case that this relaxation is going to be actually exact? It can give us the same solution as the non-convex problem, right? And it turned out that under 2 conditions, as long as 2 conditions are satisfied, then we have exactness for the convex or sparse optimization that I showed. So let's assume that I'm going to solve the non-convex facility location problem. I'm going to get the set of representatives for every j that I'm going to denote it by rj. And based on that, I'm going to do the assignment of points to the closest representative, right? So I have assumed that hypothetically I have been able to solve this combinatorial problem. I've solved the non-convex, and these are the true representatives, and these are the right assignments of points to the representatives. So the convex relaxation is going to be exact if 2 conditions are satisfied. One is that if I take every point now j, the way that the right representative or rj represents it is going to be by some threshold better than any points in another cluster, right? And that threshold is going to depend on the regularization that we have. What does it mean is that I need to have clusters in my data set where these clusters are sufficiently separated by this factor of that depends on lambda. So I need to have clusters that are sufficiently separated, one condition. And the second is that now if I look and zoom in inside one of these groups, if I look at every j, the worst representation for that j shouldn't be very far away than the best representation that I can get for it. And that means that my cluster should be sufficiently tight. The radius cannot be very large. Otherwise, if it's very large, it will make sense that I break it down into 2 pieces, then increase the encoding cost, get a much better encoding cost, but just I have increased the number of representatives by 1, which is going to be affected by a factor of lambda. Right? So under these 2 conditions, the convex relaxation is going to achieve exactly the solution of the non-convex facility location. So just to verify that how well this convex relaxation is going to perform with respect to the greedy algorithm that Amin actually talked about, and in particular the forward-backward greedy that Amin talked about, we looked at video summarization, and here I'm just looking at just the cost function of the facility location, which ideally should be lower, right? So as we change the value of the regularization, this is what we get through this relaxation convex algorithm, and this is what we get through the greedy algorithm, whether that was the deterministic algorithm that Amin talked about or whether that's the randomized algorithm. And this is for one data set TV sum, and this is for another, which is SUMMI, and the trend is quite similar. So the convex, because of this nice property, could be closer to the global optima. Okay, so one other example of the effectiveness of the subset selection generally for the problem of recognition is that, as I talked about, one of the main goals of subset selection is to reduce the computational complexity of algorithms that deal with data. So for instance, in the case of recognition, we can reduce the number of training samples, and instead of training on the entire data set, we can train a recognition system on this set of representatives. And that's exactly what we are doing here. So we are training a recognition system using all training samples versus we are selecting roughly 1/3 of the data set. And then we are basically computing the classification performance on this reduced training data set. And this is a confusion matrix which in percent, the numbers on the diagonal should be very large, as close as possible to 100, and the off diagonals, which are the confusion values, should be as close as possible to 0, right? So what is interesting is that if we look at the structure of this confusion matrix, for many cases, what we see is that using this 1/3 of the data set, we are able to get very close performance, or even in some cases exactly the same recognition performance as using the entire training data set. And in this case, for instance, it's just a little bit lower. Okay? The more interesting thing is that in some cases, actually the performance is going to go up by using these representatives. So for instance, in this example, on the diagonal, I'm getting 72.1%. There is a typo here, versus 65% using the entire data set. And on the off diagonal, which should be close to 0, I'm getting much lower confusion value. So that means that, as I said, representatives not only are going to increase the computational efficiency and memory of your algorithm, but of your recognition system, but also can improve the performance of your classifier, right? And the reason that we get this result based on inspection was that you can have very noisy labels in your training data set, and by selecting this set of representative items, we are throwing away all these noisy points that have noisy labels, and we are actually getting points that are very well representative of the distribution of the class. Okay, so this was the non-sequential part of the problem. So for the next part, what I'm going to talk about is how we can incorporate the sequential structure of the data into the facility location class of objective functions and develop this class of sequential summarization algorithms. And why is this important? Because, as I'm going to show in the case of procedural learning from instructional data, it's very important that not only we recover the sequences of key steps or key actions that need to be performed in order to achieve a certain task, but the ordering it should be recovered and is going to be important. So let's generalize the facility location now to the sequential subset selection. So what I'm going to take is a setting that my target set now is going to be a set of sequential items, y1, y2, up to y capital T, that they arrived in time. And then my source set is going to be a set of items that have these pairwise transition probabilities. So they have transition probabilities between them. So the goal is not only in addition to the previous case that I wanted to recover representatives that well encode the data and they have a small cardinality set, but also here I want to recover a sequence of representatives, R1, R2, up to RT, which are the representative assignments for Y1 up to YT, so that these sequences of representatives have a very good dynamic compatibility according to these transition probabilities that I have in my source set. So let's see this through a toy example. So for instance, look at y1, y2, yt as my target set, and x1, x2, x3 with this particular transition probability between them. So if I take this sequence of assignments, r1, r2, r3, to be 1, 1, 2, which means that y1 is assigned to x1, y2 is assigned to x1, and y3 is assigned to x2, then there is no transition in my sequence. I have a transition from 1 to 1, but I don't have a transition from 1 to 2, right? So that's something that I ideally don't want to select. On the other hand, if I go on the right-hand side and I look at the sequence of assignments 1, 1, 3, then I have a good transition from 1 to 1 and then a good transition from 1 to 3. So that's something that I prefer with respect to the one on the left-hand side. Okay? So how we can achieve this notion of dynamic compatibility? So I'm going to do building on the potential function that I defined in the previous part, which in the previous case, my potential function was a product of an encoding potential and a cardinality potential. Now it's going to, I'm going to multiply it by a new potential function, which I call a dynamic potential, right? And that's going to measure the compatibility of the sequences of representatives, y1 up to yn. So how we are going to select this in this case, for instance, in the NIPS paper that we published last year, what we took is, let's take an n-sorted Markov model for the dynamic potential function, which is going to be that, well, the representative at time t is going to depend on the representative at time t minus 1, t minus 2, up to t minus n. So it's going to be an n-sorted model, right? To the power of some exponent beta that is going to put a trade-off between these three terms again. So I'm going to apply the same trick, which I'm not going to show, which is let's define this binary optimization variable zij's and then cast the potential function in terms of these assignment variables and take the logarithm of the potential. So that's going to lead to this maximization where the first two terms are exactly the same as before. So notice in the previous case I was doing minimization. Here I'm going to look at maximization, so that's why the minus sign. But then there is this new term that I have that is going to measure the dynamic compatibility of the sequences of representatives. So what does this new term mean? It means the following, that let's assume that yt minus 1 is going to be assigned to be represented by xi, and yt is going to be represented by xi prime, right? So that means that the product of their assignment variables is going to be 1. So in this case, to maximize the potential, I need to have a large transition probability from I to I prime, right? So I'm going to select the sequences of representatives so that for consecutive time points, there is a high transition probability from one item to the next. So this is again a non-convex optimization. But in addition to the binary constraint, in the previous case, there is an additional reason for non-convexity, which is the product of these two assignment variables. And the fact that these transition probabilities are not necessarily symmetric, so once I put them in this big matrix, that's not going to give me a negative semi-definite matrix, right, in general. And it really doesn't make sense to convexify it in this case because we are going to change the structure of the transition probabilities, and that's not good. So the approach that we have taken so far to solve this non-convex problem is basically to use a maximum message passing algorithm to optimize this cost function. So roughly speaking, in the case of maximum message passing, what we are going to do is to define the so-called factor graphs. These nodes are variable nodes that correspond to the optimization variable zij, and then we are going to have these factor nodes. And each of the factor nodes correspond to one of the terms in the objective function. And the idea of maximum message passing is basically pass messages between factors and variable nodes until convergence, right? And at convergence, we are going to get the optimal set of assignment optimization variables, zij. And once we get them, then the problem is done. We have gotten the set of representatives and assignments of points to the representative sets. And this is a synthetic example that shows basically the performance of the method. So we have generated data from a hidden Markov model that has 50 states, and in this case, hundreds of samples. And this basically looks at the dynamic cost, which is the dynamic compatibility term that I talked about. And ideally, this should be lower. And the result of the sequential facility is actually much, much lower for a variety of different number of representatives compared to the DPP variance and the greedy method and the convex relaxation of the facility that I talked about, right? Because it naturally is going to incorporate the dynamic compatibility of the items. And it also achieves very similar encoding to basically these other algorithms. So in terms of application, one of the applications that in my group we have been interested for sequential facility location is the problem of procedural learning from instructional data. So what is procedural learning? So today we have access to large number of how to do videos. A couple of nights ago, I actually searched on YouTube for the phrase how to, and we got around 500 million results or hits for just the phrase how to, right? And then you can narrow it down with how to perform CPR, how to change a tire, how to assemble a device, and so on and so forth. And it turns out, for instance, once I look at how to perform CPR, I'm going to get a large number of videos. Say, in this case, I got actually a few nights ago around 100,000 of results for how to perform CPR, right? So the goal of procedural learning is actually if we can get this vast amount of data from a same task, and we produce this compact summary of the procedure that what are the key steps to perform CPR, and also how we should perform them, and what is the right sequence and order of the steps that should be performed to achieve that certain task. So the way that we address the problem is as follows. So we are going to get all the videos. So I'm going to search for how to perform CPR. I'm going to get this K video from the results of the YouTube. So the first thing that we are going to do is to break down each of these videos into these super frames, where each super frame is basically a shot or segment of the video that consists of almost the same motion and the same activity, right? And the reason that we are working on these super frames instead of frames is that working on frames is going to be wasteful of computational time because every frame and the next frame are going to be very similar to each other. So then what we are going to do is to extract features from each of these super frame segments, right, which are called H1, H2, up to HT1 for video 1, and so on. So for every video and for every segment in a video, we are applying this deep learning architecture that actually we have worked on and developed in our group for the particular purpose of summarization to extract features from each videos. And we are going to get these time series data for every video, right? Next, what we are going to do is to fit a Markov model, a hidden Markov model, to these feature representations or to these time series data. And these states now are going to correspond to a variety of sub-actions in each video. Some of them are going to be relevant to the task, and some of them are going to be completely irrelevant to the task. They could be the background motion or background activity. And there is basically a common set of states across all the videos that correspond to that procedure, right? And the goal would be to recover a subset of this Markov chain or Markov network that well represents all our video data. So next, what we are going to do is to apply this sequential facility location to every video that we have. So I have this as my source set, which is my set with transition probabilities. And this is going to be my set of sequential items. So we run the sequential facility location, and we are going to get this set of assignment vectors, right? That this point is going to be assigned to which of the states and which of the states and which of the states, right? Then I'm going to repeat this for every video that I have in my data set from the same task, and I'm going to get another sequences of representatives, right? There is no guarantee that they are going to give me the same sequences of actions. So in order to extract the common sequences of actions, what we are going to do is to run a so-called sequence alignment method that basically comes up with a single summary or a single way of performing the task. What is going to be a subset of this chain that is going to well represent the entire data set. Okay? So I'm going to go from these sequences of representative to a single one. In a sense, I'm running a sort of a consensus problem here. And once I have gotten this set of states, a single set of states, we are going to map them into the closest segment in each video to give us the summary in terms of visual representation, or basically we are going to map it into this so-called object-verb representation that, for instance, x5 is going to be mapped to this check response, x2 is going to be mapped to open arrays, and so on. And this is going to be, in the case of natural language description, the sequences of actions that needs to be performed in order to do CPR, or equivalently, I can just map these into segments of the video and get basically a summary and the order of the sequences of steps in terms of visual representation that needs to be performed. So we looked at these instructional video understanding and instructional video summarization on a data set that consists of 5 different tasks and 30 videos per task. So the tasks are how to change tire, how to make coffee, how to perform CPR, how to jump a car, and so on. Right? And these are basic, and what we are going to look at is once we get the summarization result, we are going to compute the precision and recall with respect to the ground truths of how we are going to perform that sequences of actions in order to achieve a certain task. And once we have gotten the precision and recall, then we can compute the standard F measure or F score that should be higher as possible. So these are basically the results that we got. So let's look at DPPs, and then these are 2 variations of DPPs, one called Markov DPP and sequential DPP. So the idea of Markov and sequential DPP is that you're going to break down your time series data into pieces. You're going to do subset selection in the first piece. You get a set of representative. Then you are going to condition on the first piece and then select the sequences of diverse point with respect to the first part, and so on and so forth. This is not really a sequential summarization, but to some extent tries to incorporate the sequential structure of the data by breaking down the video into sequences and running sequential DPP on each piece, right? And this is basically the convex relaxation that I talked about in the first part of the talk, and this is the sequential facility location that I just presented. So if you look at all these methods, all the first 4 methods that don't have any notion of dynamics, the performance are roughly speaking the same, right? So across the data set, this is getting 0.58 on F score, 57, 57. So very close in respect to each other. But once we incorporate the dynamic compatibility and we look at the results of the sequential facility, then the performance actually jumps a lot across the data set. Which shows that exactly what the point was, that we want not only these informative keyframes or key segments, but also how they should be performed one after another. And these are basically 2 qualitative results of performing different tasks or actions. So the top one is how to perform CPR, and this is the result of the automatic methods that we got, and this is the ground truth. So not perfect, but say for the second action, after the second action, we have gotten the order and the sequence right? And similarly, another result for how to report a plant, where we have basically missed on the second and the third step, but basically the order of the rest and is quite right. And this is actually an open problem. We are still actively working on it to actually improve these results and get much better results. And something that I'm not going to spend a lot of time is basically in the last CVPR, we looked at this sequential summarization by doing this approach in a sequential manner, running the sequential summarization piece on piece on the sequences of data instead of doing the centralized algorithm. So to summarize, it's really important for summarization algorithms to achieve as close as possible, to be as close as possible to the global optimal solution. And in the first part of the talk, I focused on facility location, and I showed that we can develop sparse optimization algorithms for it that are efficient, and they, under certain conditions, they are actually going to be exact, achieving the global optimum. In the second part, I talked about the fact that sequential data form a large part of big data, whether they are videos, speech, audio, and signals, and so on. And it's important to incorporate the underlying dynamics of the data and look at the data from the following perspective, that not only I want to select representative, but the order matters a lot. And what we did exactly was to take the same facility location that we developed and then now generalized it to handle sequential data. And I talked about procedural learning from instructional video as an important applications of these tools and techniques. And one of the interesting results that we have recently worked on and is close to publication is basically under what condition the sequential facility location is going to be a submodular function. It's not necessarily is going to be submodular, but under certain condition we can show that this is going to be submodular, so how we can develop fast, greedy algorithms along the line of what Amin talked about in order to solve the problem, instead of the maximum message passing algorithm that I talked about. And the codes are available on our website, and that's all. Thank you. Any questions? Do you want to set up your... You don't need the HTML?
Yeah, I think.
Okay, good. Good. Yeah. Sensitivity to outliers. Yes. So let me actually repeat it because it's going to be recorded. So the question is, how about the sensitivity of these algorithms to outliers? So there is a version of the first algorithm that I talked about that actually what we have done is to incorporate this notion of a point in the source set that could become a representative of these outliers, in a sense. Yes, that's true. As I talked about in the case of DPP, so for instance, DPP could be prone to outliers. And many of these subset selection techniques could be prone to outliers. So what we need to do is to modify the cost function in order to incorporate basically the handling the outliers. And what we did in the case of the DS tree was that basically we added a node to the source set that could act as the representative of the so-called outliers. If the encoding cost is going to go up to, above some threshold, then all those points that are not really the inliers are going to be assigned to the so-called outlier representative. So that's a very good question. Yep.
Okay, shall I start? Okay. Hello, everyone. Good afternoon. I'm Amit Roy-Chowdhury. I'm at the University of California, Riverside. I'm a professor in the Electrical and Computer Engineering Department. So we've heard two excellent talks by Amin and Ehsan about the various tools that could be used for summarization. I will finish off this tutorial by trying to provide a link, as best as I can, between the tools and some of the applications to the problem of video summarization. I will start by giving an overview of video summarization, and I will then give some specific examples, including some results on how some of these methods work, how well they work, what are the problems still, and so on. A lot of what I'm going to present is work done by my graduates, my excellent graduate student Elhamifar, who is sitting here. If you want to discuss in detail, I'm happy to talk to you after the tutorial, or you could talk to Elhamifar also. He has done excellent work in this area. I'd like to start off by describing the title, Beyond Supervised Learning and Incidental Supervision for Video Summarization. For those of you who have been in the field for some time and who've studied the literature on summarization going back, not just a couple of years, but maybe a couple of decades, summarization is not a new problem. A question that immediately comes to mind is, why supervision? Summarization was not traditionally dealt with as a supervised computer vision or image processing problem. There are lots of methods in summarization which are completely unsupervised. You essentially have a data set and you identify what are the frames or what are the shots in that data that best represent it. So the question is, why do we want to look at supervision? So let's look at the recent history of this field. Over the last few years, there has been a trend towards developing more supervised methods for summarization. What advantage do they have over unsupervised methods? If you have supervision, if you have a video segment and you have people labeling that these are the frames or these are the shots that are most relevant to a summary, and you do this over lots of videos, just like the advantage we see in supervised learning over unsupervised learning, or unsupervised estimation in general, we see similar advantages in summarization. However, it raises two important questions. One is the traditional question in all supervision: who is going to give you the supervision? How much supervision do you need? A second question is, if you are trying to do supervision on a video and trying to identify that frames 7, 23, 309, and so on are important, it's an extremely tedious job. I have had undergraduate students doing some of the labeling, and they complain about that kind of work. It cannot go, it's just not a scalable problem. So therefore, we want to take advantage of supervision, but we do not want to have a method which relies on a very, very tedious supervised learning phase, supervised labeling phase. So that is where the term incidental supervision comes in. And I'm going to give some details about how we can do this for the summarization problem. I do not want, so the first couple of slides are very much a repetition of what Ehsan just presented, in the sense that why do we need summarization? There is so much of data, and we need to somehow summarize it so that we have a manageable amount to handle. This is something that I would like to say that it's a little different from what was presented, which is in a network of cameras. So we at UCR, we have a facility. So we have a facility where we have those cameras. They are not set up by the police department. They are actually an experimental setup. So we have a setup of network cameras that can be controlled. These are PTZ cameras. We do not run them all the time. They are run only for data collection, for pure experimental purposes. But if you look at the data collected by these cameras, it's easy to be overwhelmed by the amount of data that is coming in. And that leads to that leads to the question of how do you summarize, not just from a collection of videos that you download from the internet, let's say, or a movie. How do you summarize from a collection of cameras, from a network of cameras? And I will talk about that towards the end of this presentation. I apologize for why the slides are cutting off. I actually have no idea, because I see them perfectly over here. But if there's, I could try to play with it. Or I could just go on and, do you want me to try that once quickly? Okay, let me. Let's see what this did. Is this better? Oh, yes, it is. Let me actually put it into. Nope, it actually made it worse. That was the highest resolution I had. I'm just going to, in the interest of time, I'm just going to. Yes. Tell me. Oh, to do it over there? Okay. Okay. Let me see. Okay, duplicate these displays. Oh, now my, Okay, that's good, right? Yeah. Okay, so one of the things I will be talking about, a little different from what was presented earlier, is summarization in a network of cameras. But before we get there, let's start with a quick introduction of the problem, and I'll try to link some of the tools that we have been using to what Ehsan presented, and a little bit to what Amin presented also. So the problem of summarization is that we want to get a brief overview of the main parts. And as I've said a little bit earlier, we want to take advantage of supervision. Summarization could be treated as a completely unsupervised problem, but we want to take advantage of supervision, but we do not want to overwhelm the person who's providing the supervision with extreme amounts of tedious work. So that is where the incidental learning comes in. All of you, I assume, are familiar with the basic idea of supervised learning. So I have a system that is trained to recognize what a duct looks like, and then given a test image, it should be able to recognize what it is. What does beyond supervised learning means? So most of the existing methods that we have for supervision today have this assumption, which is infeasible, as I've mentioned quite a few times, of extreme amounts of labeling. And here is an example that 5,000 users working 24 hours will take 1 month to label the Google image database, which has the 425 million images. So if you just scale this up and now think about it from a summarization perspective. And that leads us to the question of incidental summarization. This was a term that was coined recently in a paper at AAA. So the idea is there are signals that are available to us that we can use automatically without increasing the level of the level of labeling effort provided by a human in order to provide the supervision. So we want to utilize those signals that are available, and because of which we do not require too much of extra effort. In some ways, you could even think about this as a combination of machine learning approaches with physics-driven approaches. So if you have a physical model, if you have a reasonable physical model of the environment, how can we leverage that physical model in order to reduce the supervision? So I'll talk about some of these as we go along. The talk is divided into two parts. First, I'll talk about the single video summarization. So you have a single video, and I want to summarize that. How do I use incidental signals that are available? How do I do incidental supervision in order to summarize a single video? I'll talk about collaborative summarization. This is similar to what Ehsan just talked about, with actually using some similar methods also. And then we'll talk about weak supervision for video summarization. I'll define what those terms exactly mean. They are used with very different meanings in different contexts. In the second part, I'll talk about multi-video summarization, where the idea is I have a collection of videos, and I want to summarize all of them. This collection could come from, for example, the web, a video database. So you could, for example, look at CPR videos, and how do I come up with a summary, not of each individual video, but of the concept of CPR. And lastly, how do you extend this to a network of cameras where you also have a collection of videos? There is some correlation between them. It could be an overlapping network where there is obviously correlation, or it could be a non-overlapping network where there is also implicit correlation. The same car moves from here to here. How do we exploit that in order to do summarization? Okay. I'll start with some preliminaries, a lot of which has already been presented, and just to remind you, and this is done also to somewhat fix the notation that I'll be using going forward, but the ideas are not very different. So we have, actually, is there a pointer somewhere? No. Do you have one? Okay, thank you. Okay, good. I don't need to use. So the first part here is essentially a a cost function of the data, and then you have from D, and this is the summary that you are creating. So you have a dictionary D, and from there you are choosing some of the elements, and then you have a sparsity constraint. So this is, the first term is a reconstruction error term, the second is a sparsity term. Again, very similar to ideas that both Amin and Ehsan have already talked about. A little bit more detail about this. So I have the data. So these are the frames over here, and you represent these frames in terms of a matrix. It could be the raw features. It could be some features you obtain from a learned CNN, or however you want to extract these features. And then this is an example of the matrix C. So for example, if you have a whole row of zeros, let's say the third row, then the third frame doesn't contribute to the summarization. So this is the structure, this is the reconstruction term, this is the sparsity term, and you may want to relax this L0 norm to be an L1 norm in order to make the problem, the optimization problem, more tractable. Okay, so these are essentially the same ideas, but I will be, so the reason I put these up is rather to fix the notation going forward. There are a few assumptions that we do make, and I will talk about how we can relax these assumptions as I describe the different parts. So we assume that the videos are given beforehand. So this is not, so none of this work is on streaming videos, unlike some of the things that were just presented. Many of these methods can be adapted to handle streaming videos, and I'll talk about how we can do that, but the details that I will go into do not handle streaming videos. The basic processing unit for the summarization is a video shot. So you have a few frames of video, and again, this is an assumption because you could also build a summarization algorithm by taking individual keyframes. Each video shot will be represented by a feature vector. For the purpose of the results that I show, there will be the C3D features. Again, they could be replaced by something else. And in our methods, user preferences are not considered. So I might want a summary from a particular, even for the same video, I might want the summary to have a focus on a certain parts, while someone else might want to focus on some other parts. We do not have that aspect here, so the personalization, but again, I will talk about how that can be added in some of the optimization methods that we'll discuss a little bit later. Okay. So incidental supervision for video summarization. This is the slide that gives the overview of the different things that I'll talk about. We'll start with single video summarization, and the first topic I'll talk about there is the collaborative video summarization. What does that mean? So this is a summary of a single video. However, if I take a single video of, let's say, an Eiffel Tower, or a video of an Eiffel Tower, someone goes there, they take a video. If I know that topic, that this is a video of the Eiffel Tower, can I leverage the fact that there's a lot of other data on the Eiffel Tower that is available that could be leveraged in order to summarize even that one video? So here, let's go back to the idea of incidental supervision. The supervision here is coming from the fact that there are lots of videos of Eiffel Tower. So I get a video of an Eiffel Tower and I want to summarize it. I know that topic, that this is of the Eiffel Tower. And I also know that this particular class, Eiffel Tower, there are lots of other videos. And those other videos can provide me incidental supervision to summarize one single video. Okay, so this is a little different from the case of the multi-video, where we'll revisit the same problem, but there we would look into summarizing a whole collection of videos. So the incidental supervision here comes from the fact that that label that is provided, Eiffel Tower, there is a lot of other data that is also available. So this is the problem statement. So finding a sparse set of representative and diverse shots that simultaneously capture the important particularities in a given video, as well as generalities identified by a set of topic-related videos. So you have the topic. So the topic is what is providing the incidental supervision. And these topics are actually not hard to come by. All that you are providing is a label, Eiffel Tower, to a collection of videos, or birthday party to a collection of videos. And they are usually not very hard to get. The basic idea is to exploit the visual context from these topic-related videos. And we build up, and what the method that I'll talk about builds upon collaborative techniques from information retrieval and language and natural language processing methods. So how do we go about doing it? The mathematical formulations that I'll talk about, most of it has been presented in greater depth by Amin and by Ehsan. Especially, it was in fact, many of those were just described by Ehsan. So I'm not going to go into each and every single detail, but I will talk about how we develop these optimization functions and how we actually do the optimization. So this portion is the representative set. This is a reconstruction error. If you remember, we had a reconstruction error term and a sparsity term. So this is the reconstruction term, and this is the sparsity term. Why do we have two parts? So the first part is for this video that is specific to the one that I'm trying to summarize. The second part is to the other videos that are related by that topic. So that is the second part. This is a diversity part that tells me, again, that from the video that is specific to what I'm trying to summarize, and from the other videos that I have collected that are related to the topic, I want to have a diversity term. And this particular part combines, it's a consensus term, that combines the information from the topic-related videos and the specific video that I'm trying to summarize. So if you did not have the topic-related video, this term would go away. This term would go away. This term would go away if you even wanted to have a diversity term, and this term will go away. So you would be left with the rest of the terms. But by bringing in this part of the topic-related videos, you have a very similar optimization function, but you have this extra term that is now included in this optimization. The question is, how do we solve these optimization techniques? So there could be ways in which we could do this. One of the approaches that we have described based on some recent work is on using the ideas of half-quadratic approximation. In the interest of time, I'm not going to go through this in detail, but it is an alternative. Okay, first of all, you have the original objective function. So if, let's say, we take this simplified function, you augment that optimization function. This is an augmented optimization objective function. And this P is determined by a term that is designed like this. And then we alternately optimize between these two terms. And this alternate minimization that you see over here, so you optimize over P and then over Z, and you iterate from one iteration step to the other. This is one of the ways in which these kinds of optimization functions could be solved. I'm not claiming that this is the only way to do it, but this is definitely one way in which you could do it. Now, coming back to our problem, we have this optimization function, which has the video that I'm trying to summarize and all the other videos that are providing the incidental supervision. So I combine those parts together. I have this augmented cost function. And from the augmented cost function, if you see over here, I introduce this P and Q terms as part of the augmented cost function. And from this augmented cost function, you can solve this kind of an optimization problem. Yes?
So what is the distinction between the term that you call diversity versus the reconstruction? Why is that needed?
So this diversity term allows you to select a collection of frames that do not look similar. So you're doing this over other videos. So you could have frames that look similar to, so let's say even if you did not have other videos, if you just even took one video, you could come back and collect very similar frames. And they could still be part of the solution methodology. So this basically is a term that says that frames that are similar, that are still chosen by the reconstruction term, are removed by the diversity term. The advantage is not huge, but it does get rid of some similar frames that still come through the reconstruction term.
Do you have any particular assumptions on the D and also the Z, or they are unmistakable?
So the D is designed in a certain way that so here you have these terms which are how the diversity regularization functions come up. So in terms of particular restrictions, you could put particular restrictions like the similarity that you have. So the similarity that you have between the frames, that could be essentially something that you encode in that term. Okay. Maybe we can talk afterwards. Yeah, okay, yeah. So, but it's a good question in the sense the diversity term adds a little bit to the results, but it doesn't change the result a whole lot, yes. But you could include that term in our, it does improve the result a little bit. So here, this is the overall optimization method using the half quadratic optimization. So you optimize over P, Q, and R. So just to remind, since we lost the signal. So these were the P, Q, and R terms that were introduced as part of the augmented cost function. And then you optimize over P, Q, and R, and you optimize over Z, and you iterate over this. And this will give you a locally optimum solution. Here are certain results. So what we see over here, again, I do not have detailed statistics in this. If you want, I do have some backup slides that we could go over. But the idea I wanted to bring out is the advantage of having that extra level of incidental supervision. So we have, so this is at the top is a standard method of summarization that we compared with, while here is the bottom are the results that we obtain with these topic-related context, the incidental supervision that I was talking about. And what you can see over here is that all of these frames are essentially of the Eiffel Towers, and these are representative frames from the shots in the summary. While in the normal summary, if you just took a video, if there was a person just talking at some point, that does come up because you want to reconstruct that particular summary of that video. So this is one way. Now, is this the best way? There might be a reason why I might want to have a frame like this. However, this is an alternative way of doing the summarization where the information, the context information that comes from the fact that there are other topic-related videos could be used to provide this kind of a summary. I'd now like to move on to the next one, which is the weakly supervised summarization. This is similar to what we had in the first one in terms of the problem definition. So I have a weak label that is provided, and I want to summarize a single video. So here, so in the first one, the idea was that we could obtain information from other topic-related videos. Here, the idea is we again have some topic information. So for example, that in the training set, I have given a set of videos, I learned what aspects are important within a category. Again, the supervision here is not asking a human, a person or a group of people to say that these are the important frames. It is basically giving a set of videos that these are videos of birthday parties. These are videos of some sport. And the system, and you design a system, which in this case is a particular architecture of a neural network, which learns what are the important categories. So this is a way of identifying the parts of those videos that are important. And then, given that you've learned what is important, these important scores are used to guide the summary for the test video. So if I have a set of videos of goals scored in the soccer game, the system learns what it means, what are the important things about those goals scored. And then if I have a test video, it extracts a summary based on what the system has learned. How do we go about doing this? So I have so this network has learned the characteristics. So we leverage multiple videos belonging to a specific category. So again, this is side information that is coming in based purely on the topic. I have a topic of soccer games or penalty shots in soccer games. And I learn from there what is important about it. So there's a set of input videos, and then there is an importance map that identifies that these are the important parts. And this learned model is used to find the important segments that have the maximum influence on the model output. So in both of these situations, what we have done is we want to summarize a single video, and how do I get supervision for that single video with minimal additional effort, without asking a bunch of people to go in and label that these are the important parts of the summary. So that was essentially the main focus. So the advantage over here, so again, I'm just giving you some anecdotal examples. The plots are there in the papers or as backup slides if you want. So here is again a comparison with a standard a recent approach. And what we see over here is that we identify frames that are more relevant to the topic. For example, this was base jumping, that are more relevant to the particular topic by learning what is important in those videos. So if you are given a lot of videos of base jumping, the system first learns that there is something unique about all of them. And based on that, it identifies on the test video what is the best summary to obtain. So just to summarize where we are in this, the first part of this was on single video summarization. We want to summarize a single video, we want to leverage supervision, but we do not want to make the supervision process extremely tedious. How do we do that? We can do that by taking into account the fact that there is a lot of information that is already out there. So if I have topics, for example, which are not hard to come by, I can get similar videos on those topics, and then I could identify some correlation models. That is what essentially both of these are trying to do between all those topic-related videos and use that on the test set. Now I move on to the problem of multi-video summarization. Here the idea is not to summarize one single video, but to summarize a collection of them. So I have a collection of videos. The first part of it is when I have a collection of videos for a particular topic. So I have a collection of videos of penalty shots in the World Cup. I want to summarize all of them in some manner. And the second part will be on the camera network. So in terms of the diversity aware, so the question, diversity aware, the multi-video summarization, the question we ask is, can we generate a single summary from all the videos without any manual supervision? The idea here is that because we have a collection, again, there is incidental supervision that is available. So a video 1 provides supervision for video N and vice versa. And they come in because they are all related to the same topic. Now we are making an assumption that, that all the videos are actually related to the same topic. Now if you have videos that are noisy and and then you have lots of them which are not relevant to the topic, you run into problems. But that's an assumption that we are making. So the problem statement can be represented in this way. So I have M relevant. So this relevant is an assumption that we are making. M relevant web videos, and they could be represented in terms of their features. So I have a feature descriptor of this form. And the output is to find a summary that conveys the most important details. So introducing, so there is something wrong. I don't see this in this form over here. Anyway, so introducing the diversity of multiple videos, so the incidental supervision. So let's look at the part of this cost function over here. So the first part is a reconstruction error term. This is so if we go back to the first slide that I had, or one of the first slides, there was a reconstruction term and a sparsity term. So here is a reconstruction term, and then this is a sparsity term, and then you could add a diversity term in order, as part of this optimization function. And how do you design this diversity term? One of the ways in which it could be done, and again, this is purely a heuristic way of doing it, and you could design a different a different diversity term to explain this. So the diversity term is a similarity between two videos, Z as part of that set, V and W. So there's a reconstruction term, and then there is the sparsity term and this diversity term. So what we are doing over here is we are coming up with a summary, but of not a single video, but of the entire collection of videos. And you see that as part of this term over here. So if you go back one slide, if you look at X of V over here, so if you look at X of V over here, this is these are the features from that collection of videos. And from there, we are designing this objective function. So the problem formulation has these terms, and then we could introduce some prior knowledge via a weighted norm term. These are, again, aspects that you use in designing the optimization functions. But the basic aspect that we had of a reconstruction term and a sparsity term could be used to design this optimization function. And then the diversity term could be added if you want to reduce the similarity between frames from different videos. Again, how do we go about optimizing a problem like this? So this is the optimization function, and again, so one of the ways in which you could do this is to do an alternate optimization. Again, there are different ways to do this. One of the approaches that we could take is an optimization via an alternating direction, the ADMM method, the alternating direction method of multipliers approach, and this again will give you a local optimum for the problem. So in order to do these kinds of experiments, we did not have access to a particular data set from where you could provide a summary of that entire collection of data. So we collected a data set from YouTube, and we provided summaries, the ground truth summaries that were obtained by a group of users. And here is a summary of the different videos that we collected. So this is available on our website, so you can go in and download the video, and you can get the results. So here are some examples of ground truth summaries that were provided. We had I think this is the category for Alcatraz. So these were the ground truth summaries from 3 different users, and you can see that there are similarities, but there are differences. For example, you can see some differences over here in those summaries. And the exemplars summaries. So for Alcatraz, so these are some of the summaries that were provided by. That were provided by our method in this particular case. And here are some summaries for a different category. So in order to measure the utility of these results, there are, of course, the subjective aspect of how good these summaries are, but there is also the objective aspect of can you compare 2 methods. And one of the ways in which this is measured is through the F measure, which is the harmonic mean of the precision and the recall scores. So you could use a combination of these 2 in order to obtain a quantitative measure of how good the summaries are. And again, here are some qualitative examples of our different categories. So this is without the diversity constraint, and this is with the diversity constraint. And without the diversity constraint, we see some frames like this, which are different still, but they have some similarities also, while with the diversity constraints, those frames are no longer part of the results, part of the subset that you select for the summaries. So again, I think it's a subjective issue, going back to your question of whether we introduce a diversity constraint or not. This is one case where we do see a difference, but I believe it's purely a subjective issue. You could reduce it, and I don't think the difference is going to be that much. Okay. Finally, I want to get to the part on the camera network. There are just a couple of minutes left. So what does this mean? What does summarization mean when you have a network of cameras like this? And here the question is, can we obtain a summary not just from a single camera, but from these network of cameras? And the incidental supervision comes from the fact that these cameras there is a correlation structure in the data that these cameras are observing. And can you leverage that correlation structure in order to get a better summary or not? So the incidental supervision comes from that large amount of correlations, both intra-view and inter-view correlations. The idea over here is to split the problem into 2 subproblems. First, we want to identify these correlation structures. These are not given to you. We don't assume they are. There could be cases where you have a calibrated network of cameras, and you actually know that correlation structure. In that case, the first step may not be required, and you might be able to get a better summary. But without that assumption, the first part is to learn the structure, and that is where this embedding comes in. And then from that embedding that you learn, which is essentially a relationship that you learn on how close different parts of these videos in different cameras are, you extract the frames that provide the best representation of that data. So the 2 parts here, so we have to learn this embedding, and we have to do the representative selection. So the representative selection we've talked about earlier, and that part is very similar to what has been talked about multiple times in this tutorial. So we have a reconstruction term, a sparsity term, but on top of it we have an embedding term. One of the advantages that this embedding term gives us is that now if you have a mobile set of cameras, or some of the cameras are moving, you could still do this summarization by learning this embedding, by learning this correlation between the different views without needing to know the topology or the sensing topology between these different cameras. So that is one of the advantages that you get by introducing this sparsity term. Without it, you will always need to know this relationship, which is fine for a fixed network of cameras. You can do it once and you can assume that that is fixed. However, if there is some change to that network of cameras, you again need to go back and learn this embedding. And again, the question comes in: how do I solve an optimization of this, solve an optimization problem of this kind? And there could be different ways in which you could do it, but one efficient way of doing this is by augmenting the cost function and then using the half-quadratic optimization approach that I talked about earlier. Here are some results on the multi-camera summarization aspect. I'll show you a video in a minute. So one of the things that we see over here that was missed in previous approaches was that there's something happening over here. So a person was looking for a book to read, and that was missed in the summaries. A good question that comes up often in multi-video summarization, and I do not have a good answer to this question, is how do you visualize the results? So these are the exemplars that are obtained, but they come from different views, from different cameras. How do you present this so that a user can get a good visualization of the summary? Because these different cameras have different views. So if anyone is interested in the visualization problem, this is actually a nice problem to work on, and I haven't seen any good solution. Okay. Anyway, let me just finish off without. So I'll go ahead without the slides. So let's look back quickly at what we have. So we talked about the summarization in a network of cameras, where one camera can provide the supervision, again incidental supervision, to some other camera. So that led to the optimization function having two parts. First was learning and embedding, which was the first part of the optimization function, and the second part was a standard summarization problem where you had a reconstruction term and a sparsity term. One of the advantages of this method is that you can do summarization of different lengths without having to redo the computation. So analyze once and generate many summaries. So one of the advantages of this method is, so that particular matrix from where you are choosing the frames, by choosing different rows in that matrix, you can generate summaries of varying lengths. This is one of the advantages that comes automatically using this method. And that's extremely important because you often need to generate summaries of varying fidelity. Because a particular, so if you remember, one of the assumptions I had initially was that the methods were not designed, whatever I have presented, are not designed for user preference. However, one of the ways in which you can bring in user preference is by being able to generate summaries of different lengths without redoing the computation. The other part, so I had a video for a camera network summary but I cannot play that. Anyway, so let me try to summarize the essence of these different methods. I started off by saying that summarization is not a new problem. It has been there for a long time, and many of the traditional approaches are completely unsupervised. On the other hand, there are approaches that are supervised approaches also. However, supervision is difficult in general. Even for a classification problem, supervision is difficult. However, for a problem like summarization, supervision is even more difficult because now you do not just say that this is a picture of a dog or a cat. You actually have to provide frames for the summary. Therefore, we want to keep the advantage of supervision, but we want to reduce the difficulty of supervision. In order to do that, what we want to do, and this has been the motivation behind a lot of the work that we have been doing in this area, has been a combination of learning-based approaches, supervised learning-based approaches, with structure that is already available in the data or a physical model of the world. And there is, so the moment you reduce the level of supervision, you are losing some information. How much information we lose, we can probably gain by leveraging upon the structure in the data or some structure in the physical world. This combination of a physics-driven and a learning-driven approach is what we have been focusing on, not only in this work, but in other computer vision problems that we have been looking at in our group. And for summarization, I've presented some results on how this could be done. Another way of looking at it, just to summarize my thoughts here, is how do you do computer vision under resource constraints? And some of the things that we have talked about on summarization, one of the resource constraints is limited resources in terms of the labeling effort. In that case, can I leverage upon information that might already be present in other sources without extensive labeling? So that is one of the resource constraints. But there are other resource constraints that could come in also. So for example, you may not have the ability to process all the frames in a video. In that situation, how do you compute a summary? These are things that I did not get into over here, but they all bring in this question, this high-level question of limited resources, which could be limited resources in terms of supervision, limited resources in terms of computation, or limited resources in terms of communication. And in all of them, how do I solve the problem that I have? How do I infer about some characteristic of the data, in this case a summary, without exceeding the available resources? So that has been the overall vision.